telling you guys about the assignment last week, I was actually thinking about the next assignment, and this first one is the lead up to this second one is the lead up to the third assignment, which is the one where you actually go into another server. And that one's all ready to go. I forgot that I split it up into two instead of doing it all as one, because that made it significantly simpler. Because everything you do in this first assignment is going to be done in the second assignment as well, or the third assignment. Everything that's done in the second will be done in the third as well, plus some more. The other thing that we're going to be doing is we're going to go back to C, and so we're going to program some more things in C. We're going to do some more C programming today. And part of what we're going to do is we're going to look at a couple of different languages, and we're going to talk about why there's different languages. So before we really start, does anyone have an answer as to why there are different languages? Yeah?
Maybe one different functions?
Yes, that's probably the most significant portion of it. And really the kind of functions that they perform are what the programming languages are good at. For example, what is Bash good at? Oh, somebody said it here. Say it louder. Executing programs. So Bash is really good at starting other programs. And that's really what Bash is primarily used for, is to start other programs. It's also really good at something else, one other part.
Maybe redirecting standard in and standard out.
Redirecting, and so it's actually, Bash is really good at not just standard in and standard out, it's all of them. So which is pretty cool. Bash gives you almost complete control over another program when you launch it. And so if you say, hey, thank you, how do I even start another program in Java? Or how do I start a program in C? Or how do I do X in any other language? So for example, if you wanted to do Java, so one of the things I think you should probably look at is how do you start another executable in Java and redirect it standard in and standard out? And figure out how many lines of code it takes and what you can do with those. And once you look at that and you look at the tutorials on how to do those, and you're like, I don't really like to do this or want to do this ever, because it's different on every system and it's not really it's difficult to do. That's why Bash exists, because that's what Bash is good at. Another thing that Bash is good at is Bash is good at strings. For example, if you've looked at the if statements in Bash, all of the if statements. So for example, if we do an if statement, if we say if, that's supposed to be a bracket. $A equals, what kind of thing should I put on the other side over here?
Monkey?
I'm sorry? A what now?
Monkey.
A monkey? Okay, I'll put monkey over here. That works. That's a good answer, actually. This answer is much better than another answer. Somebody else give me another answer that wouldn't be as good. 78. 78 is bad, monkey is good. Why?
Strings.
Strings. Bash says, hey, that equals for a string, not for an integer. If you put the number 78 in there and the variable a was the integer value 78, wouldn't be able to figure it out. Because Bash is not about doing integer math. Bash is about working on strings. Why is Bash about working with strings? Keep going.
Like if you have a big old text file with a bunch of data in it that from one program you pass it to the other and you can pass it in strings, and then you can convert it with that program, but Bash doesn't care about that.
Right, so what you're saying is very, very close. It's the standard in and standard out are what? Strings. When you have sockets, which are what standard in and standard out are, when you're connecting things, usually those sockets and those files and all of that information, almost all of that communication is done in some string form. We're not doing it in integers, we're not doing it in doubles, we're doing it in string form. And that's the reason why Bash is built around string formulations as opposed to integer formulations. And this is where we get to the thing where languages usually are built around a specific purpose. And then that language is typically very good at that purpose. So like for example, if I wanted to write a Bash script that calculated the Fibonacci number, it'd be much more difficult than for me to write a C program that calculated the Fibonacci number. Or a Java program, because both C and Java are much more integer or data oriented versus string oriented. Particularly C, because C doesn't really have string things. It only has character arrays. So that's a good thing. Let's think about Bash versus, say, C. Besides Bash being oriented towards strings, what's a big difference between Bash and C? Or say Java and C.
Well, Java and C, I would say it's object-oriented, but C, you could say there's functions.
Uh-huh.
The ability to define functions.
Okay, that's true. You could also do that in Java, and I don't know if you can do that in Bash. You might be able to. But so you just write other scripts as a function. Yeah.
C is actually assembly that run on a machine, while Java and Bash run on virtual machines.
Excellent. So that's one of the primary differences between C and the other languages. So for example, when we think about Bash, if I write the line of code in Bash, if I say, as an example, echo hello world, like so. Is that assembly? Is that ones and zeros? No. But I talk about this program or this line as being executed. How does this line get executed?
It runs the program echo from its
But how does it know that? Ah, oh, I don't know how it knows that. Well, does it know the difference between, say, for example, this? Does it recognize the ls versus the echo? See, that's a hard question. It's a different kind of question. What's going on in these is that there is a program. Bash itself is a program. That Bash language is composed of ones and zeros, and at some point in the future been compiled from some other language. So, for example, Bash is probably written in C. The Bash interpreter is probably written in C, and that Bash interpreter is written in C, compiled to the native architecture, and then it is able to look at these and look at this string and do processing on it such that echo successfully runs or ls successfully runs. That's one of the big things that how Bash works. And so Bash itself, the language, when we're talking about it, is not made up of ones and zeros. However, the program that is executing the script is made up of ones and zeros. Can you think of, instead of a C line, let's think of a Java line, because the C line is going to be weird. Let's think of a Java line that would execute, or not execute, but that would print something if the user types one particular string. So let's suppose the user types speak. So the user types speak, and let's make it so the program responds. If in Java, let's write the Java program such that if they type speak, it responds hello. So after the user types and speaks and hits enter, the program should say hello. How would you write that in Java? So some if statement, you'll say user input equals speak. Then what? System.out.print hello. And then there's another else case down here which will do something else. We don't know what that else case does. I could write that in Java, I could write that in C, I could write that in C++, I could write that in any particular language. Could I write this in Bash as well? The answer is yes, I absolutely could. I could write the same thing in Bash. What it is there's a program that's running underneath what the user is typing or the user is interacting with. In this case, Bash is the language, and the language is the thing that the program is interacting with. All languages are written this way. there are some, we just classify them in two different camps. We have some languages that work this way. And this is where it reads whatever the user input was, or whatever the line of code is, and then it performs an action. In the first assignment, the extra credit is to write a calculator, where you write something like this. You say plus 3, 4, and the answer should be to 7, I believe, is the answer to plus 3 and 4, right? You're writing a program that accomplishes this. So essentially, you're writing a calculator. If we think about, as opposed to this being a calculator, we think about this as a programming language. What does a programming language consist of? Two parts, primarily. Sorry? Once, at the very bottom, when after they're compiled or executed, they turn into 1 and 0. Now, what are the languages composed of? At the very high level, yes, input and output. You're right. You're at the higher level. I want you one level lower than methods and arguments. What's another word for methods and arguments? Yep. Say it louder. Operators and operands, and then some sort of result. Methods and data. Operators and operands. And so when you said methods and data, that's the same thing as operators and operands. If you wrote this extra credit assignment, you had something along this line in it. And the user could type some number of instructions, and your program would then execute some number of instructions with the result before the user told it to quit. And then it would quit, or I don't know, maybe it only did one at a time, but you could make it so there's a for loop and it ran multiple times. It's the same thing as a programming language. This here is a programming language, the same way that this is a programming language. The same way that Bash is a programming language. And what you're doing with these languages that operate on top of strings is we call them interpreted languages. So we have interpreted languages. How do you spell interpreted? I don't know if that's right. Interpreted or interpretation. Interpreted. A second or another a program is executing your instructions for you. Just a second program. My brain's really not working today for this one. It is interpreting the strings that you type as instructions or as things that get performed, as actions that get performed on data. The other kind, what's the other kind called? Starts with C. Compiled. What's a compiled language composed of? It's user input, or the program, user program, is converted into 1s and 0s. That the CPU can execute, that the CPU performs. Virtual private, not virtual private networks, virtual computers, virtual machines, operate in some level between the two of them. You have some, like Java is compiled to a virtual machine. That compiled language is then interpreted on top of a real machine. It does a little bit of both. But what's the result of these things? So for example, if we talk about an interpreted language or an interpreted program, how is an interpreted program going to be different than a compiled program? Something that should jump out right away. So it doesn't need to be compiled, you're right. Okay, so that's by definition the difference. But what's another thing here?
think it executes line by line, where the other one like goes through like compile and then executes.
That's true. That's what it means to compile it. Uh-huh. So an interpreted program is typically going to be much less efficient. When we say it's less efficient, what does that mean? Slower execution time is really one of the things we're talking about. Slower execution. So if we consider Java versus C, which one of those is going to have a faster execution? C. Why? Huh? Because C has an interpreter, or Java has an interpreted layer on it. Java has the virtual machine that it has to execute. That means that Java is going to have a, oh, they type the plus symbol, and then a 3, and then a 4. Let me convert that into an actual machine code that then needs executed. So usually you will get slower execution. This is not always true. Why is it not always true that you'll get slower execution on an interpreted language versus something like C?
It might not natively handle some of these things, so like Bash doesn't really do well with numbers.
That would be an argument for it being slower than that. It's more slow, even. I'm saying the opposite. Why would you ever get why would an interpreted program ever be faster than a compiled program? When would an interpreted program be faster? Faster execution, not faster to write, because that's the second question. Yes.
Eventually, at some point in time, our program becomes a lot faster than interpreted, but for the very beginning, something like that.
I like what you're saying. The answer is going to be no. What you're saying does have some basis in fact, but for the most part, it doesn't matter.
The interpreted language is
Yes, that's what I was thinking when you're talking about complexities. Let's suppose that you need to sort 1,000,000 integers, as an example. And in Java, you can call the sort function on those 1,000,000 integers. And that Java program is going to be written in quicksort or merge sort, and it's going to be exceptionally fast. If you haven't taken 310 and you haven't looked at 560 at all, this is what 560 does. 310 talks about is what is the complexity of a program. So, for example, Java's merge sort or quicksort is going to be something that we call a big O of n log n. That means its worst running time is going to be something along those lines. But if you're writing a C program, C doesn't have a quicksort library for you to use. And so let's suppose you write your own sorting algorithm. Now, how many people have written their own sorting algorithm? 7 of you. Good. Have you written quicksort? Yeah? So some of you have written quicksort, which is good. If you have written quicksort, excellent. If you haven't written one yet, quicksort is not where you start. Quicksort is relatively difficult as far as sorting algorithms go. You start with something like bubble sort. Bubble sort has a complexity of O of n squared. And so if you're just writing your first C program, you get O of n squared, which is much slower than O of n log n. You get the 1,000,000 integers. Your C program is now going to be significantly slower than your Java program because of this complexity. The library that is provided by Java is going to be significantly faster. This is not just talking about implementation time, which is the next question. Let's talk about implementation time. If, for example, you want to write a web server and you're using C, how much of the code do you have to write yourself? Versus in Java, you say, give me an HTTP header. And it goes, okay, here you go. You don't have to write anything else. Those headers take the implementation time significantly less. So even if you lose a little bit of speed in the execution time, you gain a lot of time in the implementation time. So some interpreted languages are much better than that. Which leads us into, what in the hell is C++? What is C++?
It's barely above assembly, but still faster than
Almost. Almost. It's closer. That's better. So it's not barely above assembly. It's barely above C. Is what you C++. So what is so C++ is barely above C. It's C with extras added on. It's not really C with extras added on. It's kind of a reworking of what C should be. But it's C with object-oriented programming added on. The other thing that you get with C++ is you get a number of libraries, particularly if you use something like Boost or the C++ 11 standard libraries offer a lot more information. So for instance, you get Boost, which will give you quicksort, the same way Java gives you quicksort. However, C++ is also directly compiled to the hardware. What's a benefit of the interpreted besides implementation time because of libraries that you don't necessarily get with, or you don't get at all with compiled programs? You know. Go for it. Most interpreter languages are machine independent. It doesn't matter which machine you execute them on. So for example, Java, you write one line of code in Java, you write the console or system.out.println on Java. That's going to work the same on a Linux box running an Intel x86. It's the same as it's going to work on a Unix box, a Sun OS box running on a I don't know what the chip they have on Rohan is. The same as it runs on your OS 10 box on an Intel chip. The same as it runs on an Amiga or on your smartphone on your Android. And so you get this cross-platform functionality that you don't get with other things. So when we talk about that cross-platform functionality, let's think about Java. What big project? Does anyone know a big project that has recently used Java for a while, and why did they choose Java? Why do you think? A really big project that everybody uses on an everyday basis, or nearly everybody uses on an everyday basis. So Twitter has Java APIs. It's not written on Java. More fundamental even than Twitter. More fundamental than that even. Huh? Adobe? Yeah. Android. Android is written in Java. It's not all written in Java. There's some C++ and some C. But it's primarily applications are written in Java. Why? How many Android devices are there? Lots. How many Android CPUs are there? Lots. How many iOS devices are there? There's one every generation, right? How many Apple devices are there? How many MacBooks are there? One every generation. There's one MacBook every generation. They just make different sizes of screens and hard drives. Everything else is identical. Maybe RAM is improved. So why does Apple choose to make it so that there's only one of something versus Android chooses to make lots of things? And why does Android choose Java?
Apple chooses to make one thing so that they can optimize their code as well as they possibly can on their device, whereas Android has to use Java because there's Intel on the device.
Correct. And so this is an example of, if you wanted to write C for Android, you have to make sure that you write that C program that runs on a lot of different types of Android devices. Maybe 1,000 of them. If that C code doesn't work on all 1,000 Android devices, you're shit out of luck. Whereas Apple products, they go, yeah, we don't write in C, we only have one anyways. Go for it. Right? And so what results is that it becomes much more, for the developer with Apple products, it's much more flexible. The language isn't as important. Whereas Android is much more important. The same thing is true for Windows applications. Used to be. What was Microsoft's answer to having many, many devices or types of devices? For like, there's Dells and there's Acers and there's HPs. So beyond just drivers, there's more that. There's another thing they offered that does this as well. They don't like Java. Why doesn't Microsoft doesn't like Java? Besides the fact that Oracle owns Java and nobody likes Java. Nobody likes Oracle. Because nobody likes Oracle. Because Oracle doesn't release patches. Yeah, it's part of it. But Java is not particularly fast. So Microsoft's solution was, okay, we'll write our own. So they wrote C#. So Microsoft implemented C#. They spent 10 years writing C#. They wrote C# to replace Java. Now Java essentially is its only location that it runs now is on Android. And Android recently, as of 6 months ago, decided to write their own version of Java because Java itself is open source, whereas everybody uses Oracle's version, and Oracle will probably be The Oracle's, I don't know how the fuck they're still alive. I don't know. Because the Oracle tried to sue Google, and Google said, well, fuck you, we'll just ride around. Politics. So Microsoft's answer to Java was C#. And so now you have C#, and C# applications run on iOS devices, they run on Android devices, they run on Microsoft devices, they run on Apple devices, they run on Linux devices, they run on servers, they run on everything that C# does. Because C# is another virtual machine language that is both interpreted and compiled. The other thing is that C# is relatively fast. Who uses C#? What is one of the biggest proponents of C#? Who is the biggest proponent of C#? Besides Microsoft. I like your answers. Starts with U. Unity. Unity does. Unity pushes C# because C# is their choice, their de facto choice of programming language for all of their Unity games. So if you've many games, primarily ones that are written for Android and for iOS, are written in C# with Unity. And Unity uses C# because it's fast, it compiles well, and it has a lot more functionality than Java does. And it also supports this kind of both paradigm with interpreting. Yes?
What is the mono? What is
Mono is C# for everything. Yeah, and Unity pays them a lot of money. Xamarin Studios is the Unity offshoot that's for profit, that doesn't make any money because nobody buys that, use that Xamarin, that Unity actually funds.
Unity funds Xamarin?
Yeah.
Oh, I didn't know
Yeah, that's the reason why C# runs on everything, because Unity wanted it to. And so this is about languages and why we have different kinds of languages and their purposes and things like that. So that's part of what the goal is to be talking about. So we get lots of execution in different places. Those are the two big points. All right, let's take a step back. We have about 45 minutes. We're going to talk about some C-specific things, because we talk about C being fast, we talk about C++ being fast, we talk about other languages as giving us other kinds of benefits. But let's actually look at what some of the things that C does. Perhaps one of the biggest things that C does for us is it gives us control. Excruciatingly high levels of control. What does this mean? What is the result of getting lots of control? We have a lot of responsibility. And if we don't know what we're doing, because we're not responsible with our C code, we will break things constantly, and we'll screw up. So let's talk about some fundamental C components, C components and C concepts. When I talk about these being fundamental C concepts, they're even deeper than just C, but we primarily teach them. So if I have my int main here, I say int x, and I say int star y equals ampersand x. This is going to be the first. This is the one of C's most powerful aspect that most other languages hide from us. This is called pointer stuff. Pointers, not pointer stuff. In C, when we see the asterisk means that the variable that it is part of in the definition, so this is the declaration here, the variable y is a pointer. It's a pointer to another variable. What is a pointer? It's a reference. What does that mean? That's another word that if you don't know what reference means, it doesn't help.
It contains a memory address for the object it points to.
So not just let's not use the word object or variable. There we go. The data it points to. So because the reason why I specifically said is because you want to think about it not as an object or as a variable, because we don't know what it is. It's just data at this point. We can treat it as anything. So we've declared this variable y to be a pointer or something. It means that the data that is contained inside of y is an address of another piece of data. Let's think about some houses here. Let's suppose that I'm looking for a person. Let's say the person I'm looking for is Mike. So I'm looking for Mike, and Mike is here. Right? Let's suppose that Mike lives in his house, because this is Mike's house. And Mike's house has the address 68,000. 6,800. That's Mike's address, is 68,000. And we have another address over here, which is 67,009, or 67,099. The address on the other side is going to be 68,001 for the houses. If we're looking for Mike, and we go into house number 6799, are we going to find Mike? Because he's not there. Do we know what's inside of 6799? No. Do I know what's inside of 6800? I do. I know that Mike's inside of there. That's because I'm omnipotent, or not omnipotent, omniscient at this point. I know where everything is. And I know that I don't know what's inside of 6801. Let's suppose that there's, in 6799, there's a whiteboard, and on that whiteboard is an address. So the address on that whiteboard is 68,000. How can I find Mike? There are two different ways I can find Mike. I can absolutely just guess and check. Now the problem is when we're dealing with real memory or real houses. Does anyone know where I live? Go start knocking on houses. I swear I live somewhere near SDSU. You'll find me eventually, right? It takes a long time. So we can either just randomly look, or we could go, if I go into 6799, I can find 68,000 and go in here and go, hey, Mike. I found Mike. So I can use the whiteboard pointer, or use the whiteboard address that tells me where Mike is, or I can use Mike's absolute address. So if I know where Mike is, I can just go to Mike. If I don't know where Mike is, I can go to the part that is pointing to Mike for me. That's what pointers do, is they point out other people or other places. As an example, or not as an example, but as a more real example program. Let's suppose this is our memory. I draw memory vertically. Each one of these rows is 4 bytes across, so that means that I can have 32 bits inside of them. The reason why I do this is because I think about programs or CPUs that have 32-bit pointers. Let's suppose that this is where variable y is. The value inside of variable y will be an address. It is going to be the address of variable x. So if variable x is down here, variable y might be something like this: 0, 0, 0, 0, 3, 7, 9, 0. 3790. That means that x's address, the address on his front door, is going to be this. Do I know anything about the value of x yet? I don't. I only know where it is. What is the value of y? Where x is. That's the way we want to think about this. The value of y is where x is. Is x inside of y? No. It's just where x is. It's the location of x. Y tells you where x is. Why should I do this? Why is this important? It can, but that's usually not the reason why. Correct, but that doesn't mean anything yet for a lot of people. Or keep going. Explain it better. So what he said is pass by reference, not pass by value. So now we have to talk about what pass by reference versus pass by value is. Let's suppose I have another function over here. I have the function int add 1. This is going to be an int star y. That's going to be y star equals star y plus 1. It's going to return 0. Let's make it 4. We have another function over here. Let me do another version of this function. These two functions are very similar. They both add 1 to y. That's the way we read it. I say, what does this line of code do? Oh, it adds 1 to y. What does this line of code do? It adds 1 to y. But they're subtly different. We have to talk about what this means here, what these things mean, and how this part here is used. So on the top here, what we're doing is we are explicitly passing by reference. On the bottom, we are explicitly passing by value. What this means is that the first one takes an address of something else. And the bottom one takes the value of that other thing. We can think about this one down here as making a copy, and this one does not make a copy. That's the way we can kind of think about this. We'll find out that both of these end up making copies. They just make copies of different things. When we see the star y here, that means get the value of the thing that you are the address of. So the thing that you find, give me the value of it. This one also says store it in that location. So for example, in this case here where we have y and x, if I called add 1 with the first one, if I call it with the first one, I could say add 1 with y in it, like so. And the value of x is going to be incremented by 1. So let's give it x of actual value here. Let's say that x equals 3, like so. So the value inside of x is going to be this. That's the binary value in hexadecimal. If you don't know how to do the binary value in hexadecimal, you'll learn that 237. This is that value in that location there. When I call add 1, this is why it says, hey, give me the value of the thing that you point at. So we look at the value of what y points at, which is this location. We take this value of 3, we add 1 to it, and we store it to that location. So that value becomes 4. That's what's occurring with this first iteration. If, however, let's suppose I try to call our second one. So we'll call this add 1a, and this is add 1b. If I try to, instead of calling add 1a here, this is what add 1a, that's the first time when we added it became 4. If instead of calling add 1a, we call add 1b, and we still want to add 1 to the value of x. So instead of passing the location, I pass the value of x, like so. What ends up happening with our second 1b here is we get a third location, which is this y here, which has the value of 3 in it. How many y's are there? 2. Right? We have this y up here and this y down here. Who does this y up here belong to? Who does this x belong to? Who does this y belong to? Let's add 1b over here. So we add 1 to that y, this becomes the value of 4. Right? Any questions about that step? Let me go back and write it again with the add 1a. We'll take a look at it again. I'm going to erase that y real quick. Change this back to add 1 for a. Now the same way that we did it the first time, where we got a new thing for y down here, or the second time for b, add 1b, we also get a second one of these things up here. You go ahead and do that. I'll go and put it up here. Here's a y. Again, we have how many y's? One of them belongs to main, one of them belongs to add 1a. We have one x which belongs to main. What's the value of this red y up here? And why is it the address of x? It's the value of mains y. The value of mains y is 00037 3790. Like so. Now when I say star y here, which y am I talking about? This red one, not this one down here. We're talking about this red one, right? I say star y, which says go to whatever this point's at. What is this pointing at? 3790, which is this guy right there. Get that value. What's that value? 3. That 3 comes out, add 1, 4. Store it back into whatever that location points at. Make that a point. So. So what's the purpose of this pointer? Versus, what's the purpose of this pointer versus this one, this value down here? Doesn't actually change the x value over here. That's correct. Keep going. More? Okay.
It allows you to create functions that
They're methods is what they become. That's true, but there's more. It's more to it than that. So that is a byproduct of what it allows you to do. It does. That's what the star and the ampersand allow you to do. But why? It does give you more control, but why? That's right. All programs manipulate data, so I'm not going to have that take those values.
is it to artificially create instance variables where you operate on them.
Possibly, but I'm not going to say yes to that. I don't know what you're thinking of. That's not the. I'm going to say that's not the correct answer.
Just to avoid encapsulation.
No, not for C. That is a correct answer. So why though? You're right about that, but why? Huh? We're almost there. You're right. We're almost there. Why do you want that? Why do you want that? Why do you want that? Sorry? What was that one over here? No. Good guess though. So we're on the right track. Everyone's on the right track. There's a fundamental concept for this though. No, not for C, because C doesn't have object-oriented programming. There's no polymorphism.
You don't have to
kind of. That's true. Fundamentally, what we want to do is we want to be able to share data. We want two functions, two or more functions, to be able to share the same piece of data. And this is where we're getting that update and so on, and these guys are talking about in the back. Really what we want is we want two different places to share one value. And the way you get two different places to share one value is to have those two different places point at a single value. Right? If you want to think about this in a physical way, right? I have a red marker. How many red markers do I have? If this entire class wanted to use this one red marker, we would all share this one red marker. The way we would do it is we would know where it is. Somebody could come over and use it and put it back, and then somebody else could come over and use it and put it back, and always be the same red marker. As that red marker changed over time, everybody would be consistent with that same red marker. When you pass by value, you're not sharing a marker, you're duplicating it. So for example, in this case here, how many Y's do I have? How many copies of that Y do I have? 2 of them. If I change one of those Y's, does it affect the other Y? Am I sharing either of those Y's? I'm not. However, with these 2 Y's, I am sharing that single value. That's ultimately what all of this comes down to, is how do I share this single piece of data? Your answer about polymorphism in C++ is true because of the sharing. And that also might be what he was talking about as well. But I don't know. So pointers allow us to share a single piece of data. How do we deal with this crap? What is this crap? When I say this crap, what do I mean? Ambiguity between what? Why? No, you're right. So I have an ambiguity between my variable names. How does C, or how does any program, know the difference between those 2 variable names? Scope. How do we define scope in C here? The curly braces here. So we have these curly braces in main. That means that when I declare this Y here, which is this guy right here, this is the scope. That means that when I refer to the name Y over here, I'm referring to that location. When I refer to the Y over here, I'm referring to this location over here. But it's not always just exactly that. And this is where it gets a little bit confusing as well. If this wasn't already confusing for me, maybe get a little bit more. Now this is going to cause a problem, but that's okay. We're not necessarily dealing with real problems right now. We're just going. What did I do there? Let's add 1A. Huh. So when I call add 1A over here with Y, I created this Y up there, right? Well, that add 1A calls add 1A. What does that do? Creates another Y. Sorry, wrong one. 3790. What does this add 1A do? It calls add 1 of A again, which makes another Y. What does that add 1A do? Calls add 1A again, which does what? Makes another Y. How many Y's do I have now? 4 of them, right? Now, which Y is that talking about? Well, that one in there. Same thing as that one in there, and that one in there. All of these function calls, and obviously this will run forever until my memory fills up and then my program will crash, correct? Because eventually this will just be full of Y's. But what's unique in this entire the program that runs forever until it blows up? What's unique here? Each y has a different memory location, that's true, but there's one thing that is unique across all of these things. Sorry? They all share the single value of x. So the x is always identical. It doesn't matter how many y's I make, doesn't matter how many times I call this function, they all share the single value x. So for example, if I wrote inside of here, y star equals, star equals star y plus 1, before that add 1, that single memory location is going to increment every single time. Until eventually either the computer crashes, or not the computer, but the program crashes, or that y will overflow into 0 or negative 1. That's what's happening. This is the concept of sharing. C gives you the ability explicitly to share. Some languages, like Java, do not. Have you seen a pointer in Java? No. But Java does actually give pointers. And the trick is, Java has two different types of data. What are the two different types of data that Java has? Primitives and objects. Everything's either a primitive or an object. In Java, everything that is a primitive passes like our add one b did. In Java, everything that is an object, passes like this. With a pointer. It just doesn't tell you that it passes like that. Why does it not matter? Why do they not have to explicitly give you a pointer in Java? Yes, but why? How can they get away with that? That's true, but why do we need it in C, or why do we need to explicitly state it in C, but we don't need to explicitly state it in Java? Fundamentally, there's something that's different between the two. There are no objects in C. In C, you only have add one b. You only have pass by value. In Java and C, the way that Java and C are the same, the way that they're identical. They're both pass by value. As soon as Java adds in object-oriented programming, they also add in pass by reference, which is what Java's other mechanism is called. So everything that Java does for objects is pass by reference. Everything they do for primitives is pass by value. So the difference between Java and C is nothing underneath the object-oriented pass by reference. Everything else is identical. When we get into C++, that's not true. C++ does not natively give you a pass by reference because it adheres to C's everything is pass by value unless you explicitly state pass it by reference. So this is that whole pass by reference versus pass by value conversation. Okay, so we want to be able to share. Once we're able to share data, we can write multiple functions that all use that same piece of data. Why do we have to have multiple functions that share a common piece of data? So it does allow functions to communicate amongst each other, but there's a specific reason why we want to be able to share specific kinds of data. And this goes in, when we do C++, we'll be able to see this as well. And why is Java shared pass by reference for its objects? That makes sense as well. When we write functions like addition, so when we write this add one function, it's relatively generic. The value of 7 is essentially the value of 7. It doesn't particularly matter. Like sometimes I want to have a counter that updates multiple times, but 7 doesn't really matter. It's always going to be 7. Is that true for everything? true for everything. What is an example of something that's not true? Things don't just duplicate. You don't just duplicate people. You don't just duplicate pens. Objects don't just duplicate. Typically, if you're going to duplicate an object, you have to do a lot of work. What is an example of something that we use regularly that doesn't duplicate in computers? So social security numbers, yeah, but so specifically for computers, something we use every day. Files, right? So if you open a Word file, do you duplicate that Word file every time you open it to save it again? No, usually you open that single file, you make some changes to it, you save that single file again. There's only one file. Can you duplicate the file? Absolutely, you can absolutely copy and paste that file and make a duplicate of it. But typically, you're not duplicating files. So when we get into C, there are certain classes of things that we don't want to duplicate. Files are one of them. So for example, in C, if I want to open a file, what do I need? Say that louder. A pointer. A pointer to what? A pointer to a file. I need a file pointer. Is the thing is that entire file inside of that pointer? But that file is at that pointer, is what that means. So for example, if I take the C word for file, I can say file here, in all caps. And I can say my text file. The variable my text file will exist in memory. Now when it's all caps like this, one of the things that it's doing is it's hiding inside of it the fact that it's actually, file is actually an integer pointer, but that doesn't particularly matter. It's an integer. You can think of this as an integer pointer, is the way we can consider this. Whether or not they keep it as an integer pointer or as an integer doesn't particularly matter. We'll talk about why that doesn't matter as well. Is the contents here in these 4 bytes? The contents is somewhere else. Do I know where it is? Probably not. I don't know exactly where it is, but I can just, since I don't know its actual address, I can just kind of point at something here. And then there's some memory here. I don't know how big this is. But this is where the contents of the file actually is. This allows it so that I only have to have one copy of all this contents. And this goes into you can reduce the amount of memory used. What if I have a 5 gigabyte video file that's a movie of some kind, and I want to be able to open it and read it? Do I want to make multiple copies of this 5 gigabyte video file? And the answer is no, I don't. I don't want to copy this around. So having one place that I can point to it for multiple locations is a good way to do it. The other thing is, do I want to read all of those 5 gigabytes off the hard drive into my computer program? Most everybody probably has 5 gigs of RAM now, but this wasn't true 5 years ago. You don't want to read the entire hard drive into this. Let's do 10 gigs. How many people want 10 gig or 10 gig file into my computer here? I can't read the entire thing. So this part here is some way of accessing all that information. Do I know what's inside of here? No. Do I know where this points? It points to there somewhere, but I know the actual location. No. I don't know. Do I need to know? Why not? Because the file does it, right? What is that concept what is the concept called when something else is in charge of it and I don't need to go any deeper? It's an abstraction. So we use methods to do it, but the concept is actually abstraction. Abstraction. What is an abstraction? What's an abstraction?
It's like a layer of code that makes it easier for another user.
Let's use the more general purpose definition of abstraction. What's the general purpose definition?
A layer that allows for more complex concepts to be made simpler.
A simplification of complex concepts. Let's just call it that for now. An abstraction layer is, when we're in computer science, is what we were saying earlier. It's a layer of code that hides the complexity below it. So, for example, we talk about files, which might be integers or int stars. It doesn't particularly matter which one they are. But I don't care what that file is. And the reason why I don't care about it is because there are a number of functions that implement all of the behavior that I need. This is an abstraction. Can I learn how it works? The answer is yes, I can. Do I want to? Usually, no. Some people in the class, and this happens a lot in beginning programming, they always go, well, why does it work that way? How do I find that out? I want to know all these things. I need to know all this information before I can move on. The answer is no, you don't. You don't need to know anything else to be able to use it. And that's one of the biggest pieces of information that I can give you to be a successful programmer. There's a point at which you don't need to know anything else to be able to use that piece of, like, for example, grep. Do you know how grep works? Do you know what it does? Do you have to understand the code that implements it? The answer is no. You don't have to use it. You don't have to care. Just stop. Some people want to go all the way deep down. Some people don't care. Some people are like, why? I don't. Whatever. That's that abstraction layer. With this abstraction layer inside of C, we have the ability to break it at will. So for example, in the file, which is a text file that looks like that, I can also say something like this. Int x equals 3 float y equals x. I can do something like that in Java as well, but what am I doing here? So what does that mean? So what does that mean? Right, what does that mean? Correct. Because I can use floats at an abstract level. A float is a number that has a decimal place in it, like 3.14 can be a float. 3.14 cannot be an integer because it has a decimal place in it. Integers can't have that. If I understand that abstraction, I can use integers and floats. I can also break that abstraction layer, and I can know that as an integer, that 3 can be the number 3. As a float, it is stored in a different way, and that's data abstraction. This file is the same kind of thing, same kind of deal. I could just as easily, instead of equals x, I could say equals my text file. I could just as easily say float y equals my text file. Is this a float? Absolutely not. But I can break that abstraction. C gives me that power to say, no, I don't care what that actually is. I don't care what that abstraction layer tells me it is. I'm going to turn it into something else. And when I turn it into something else, I can now use that as a float. And then I could say, for example, I can say y equals y plus 1. And I can say my text file equals y. What's the result of that? No idea. If my text file is stored as an integer, this might work fine. It's possible that my text file will simply point at another file somewhere else on the disk. It might point at another location that I've opened something else if I've opened two files. It might break entirely, I have no idea. How do I find out what that does? The answer is I break all the abstraction layers, I get as deep as I can, and I find out how are y's represented, how are the ones and zeros represented for a float. What does this mean to add 1 to a float like this? What does the ones and zeros in here represent? Do they represent the contents of a file, a location on disk? Do they represent another location in memory? Which parts of them? I have to break all those abstractions to get down there to understand what that code does. But I don't have to, I can stay above it. So when we look at, say, bash versus C, there's also layers of abstraction between those. So when we say that bash works with strings better than it works with integers, there's an abstraction that's in place for those strings. One of those abstractions is that we don't know the format that those strings are kept in. So if I say, for example, what is the value of A in bash? What's the answer? The answer is A, because there is no abstraction below A. In bash, A is A. That's the lowest you can go. In C, if I said, hey, what is the value of A? I can break that abstraction. What's the value of A in C? What's the ASCII value of A? Lowercase a, lower capital, doesn't matter. 60 something, right? That means that now instead of the letter A, it is now the integer 61 or 60 or 68 or whatever the value happens to be. Well, that integer is a value. Can I break that abstraction down? The answer is yes, I can. I can break that abstraction in C. In some languages like Bash, I can't break the abstraction layer. In languages like C, I can. That's why when we say C is a more powerful language, it's not necessarily powerful, it gives you more control. It's not just in terms of I can make pointers to different parts of my memory location. That doesn't exist in Bash. The other part of it is I can break abstraction level layers at will. What does Java have that C does not? Besides, object-oriented programming is the correct answer, but what is the more abstraction layers? What does C# and Java really differ at? Different abstraction layers. C# has a different layer of abstraction for different concepts than Java does. Some of them are the same, some of them are different. When we're talking about programming languages, really what we're talking about is where is that abstraction layer different? How are they broken? If we're programming in Bash and I say I want to find all of the text files that contain a string, that's one layer of abstraction. Way up here. Find all the text files that contain a string. Well, to get to that in Bash, I have to break it down and go, well, let's break down, what does that mean? Well, I have to look for regular expressions inside of a file. I know that there's a program called grep that does that for me. So grep actually implements that abstraction fairly well. I don't have to go very deep into that. What if I have to do that in C? What do I have to do? I have to break this concept of file. What is a file? File is a pointer that I have to use programs to open or functions to open that result in what? What can I do with files in C? What can I do with files in Java if we're not doing C? It's the same thing. What do I get out of them? Strings, right? So I have a bunch of strings that I can get out of a text file. Let me get some strings out of a text file. Then I have to look for another specific string. How do I compare to two different strings in C? In C, we can't use the if statement. We can't do this. You can't say, if we have a char buff here, let's say we have a char buff. We can't say buff equals hello. We can't say that. That doesn't work in C. How many people know that doesn't work in C? 2 of you, 3 of you, right? Why do the rest of you not know that doesn't work? Probably because you haven't tried it yet. But there's another reason why. Because you don't know the abstractions in C and where the abstractions stop. So for example, in C, that is a pointer. This is also a pointer. In this case here, we're saying this turns into, is the memory address 000000078 equal to 074AB900? Are those two memory addresses the same? No. Because in C, that's what that abstraction means. That's not true in Go. That's not true in Bash. They're different levels. Once you know that this is what this layer is asking, now okay, this makes sense. Obviously, that's not the same thing. So then the question is, how do I compare two strings in C?
Well, there's some methods in
There's a method in the standard library called string compare, strcmp. And we use strcmp to do this. String compare would compare those two things for you. How do we find that? How do we find that string compare if we don't know about it? Google it. But how do we know what to Google to find that? We have to find the right abstraction and ask the right question. For example, if I said, how to find a string in all the files in C as my Google question, that's going to yield terrible results. I have to be able to break that abstraction until I get to the place where I'm saying, how do I compare two strings in C? That will tell me the answer then. I have to be able to get down to that level. So really, when we're talking about programming languages, we're talking about different layers of abstraction and how to break those different layers. All right, that's it for today. Abstraction layers is the big point. We're talking a little bit about C, how C is different than Bash, how C is different than Java.